Hey everyone, anyone can write code that works, but what does it take to architect software that's truly robust, elegant, and really built to last? Well, it's all about making that shift from just being a coder to truly thinking like an architect. So let's start with that big question. What actually makes good software great? It's not just about getting the job done today, right? The real magic lies in the design principles, the stuff that ensures your code is still understandable and, more importantly, adaptable way down the line. All right, let's open up that architect's toolkit. The very first tool we're going to pull out is something called the rule of substitution. Now, this is a big one. It's all about making sure the different pieces of our code fit together in a way that's clean, logical, and, this is key, totally predictable. Now, to really get this rule, we got to do a quick refresher on a core concept, inheritance. Just think of it like a family tree for your code. You've got a base class, kind of like the parent, which has certain traits. And then you have a subclass that inherits those traits and maybe adds a few of its own. Simple enough. But here's the catch, and it is a big one. Inheritance is super powerful, no doubt. But if you're not careful, it can get messy, fast. Subclasses can start behaving in really weird ways you never expected, breaking the entire logic of your system and leaving you chasing down these incredibly frustrating bugs. And that is exactly why we need a solid principle to guide us. And that principle is the Liskov substitution principle, or LSP for short. Now, I know, the formal definition here looks a little academic, but trust me, the core idea is incredibly practical. All it's really saying is that a subclass has to be able to step into its parents' shoes, perfectly, without causing any problems or any drama whatsoever. Let's just boil it down to this. A subclass has to be truly substitutable for its base class. That means anywhere in your code that you're using the parent, you should be able to just drop in the child class instead, and the program shouldn't even notice. If you can't do that swap cleanly, your inheritance design has a flaw. So how do we follow this in the real world? It all comes down to a few key promises. A subclass can't suddenly make things harder by adding new requirements that the parent never asked for. And it has to deliver outcomes that are at least as good as what the parent promised. Think of it this way. A subclass can always do more than its parent, but it can never do less or go rogue. And here's the kicker. Your compiler won't check this stuff for you. This is a design promise that you, the architect, have to enforce. Okay, let's put that tool down and grab the next one. We've just talked about how objects are related to each other. Now, let's get into how they talk to each other. So, picture this. You're building the ultimate smart home. Sounds awesome, right? Your alarm goes off, and boom, the coffee maker starts brewing automatically. You leave for the day, and your phone tells the thermostat to turn down. At first glance, it seems pretty straightforward. But then you add smart lights and smart blinds and speakers, and before you know it, you've got this complete spaghetti mess, a tangled web where every device is talking directly to every other device. Adding something new like a smart fridge means you have to teach it how to talk to everything else. It just becomes a total maintenance nightmare. And this chaos is the perfect setup for our next tool, the mediator pattern. Instead of that tangled web, we introduce a central hub, a coordinator. Think of it like an air traffic controller. This single object, the mediator, is in charge of everything. All the individual devices, which we call colleagues, they stop talking to each other. They only talk to the mediator. The difference is, well, it's night and day. On one side, you've got chaos. Everything is tightly coupled, totally dependent on everything else. On the other side, with a mediator, you get order. Communication is organized, the components are loosely coupled, and the whole system becomes incredibly easy to maintain and expand. Want to add that smart fridge now? No problem. You just teach it to talk to the mediator, and you're done. The flow of communication becomes beautifully simple. First, a colleague, let's say the alarm, tells the mediator, hey, the alarm just went off. Second, the mediator, which contains all the system's logic, processes that event. And finally, the mediator sends out a command to another colleague, telling the coffee machine, okay, time to start brewing. Simple, clean, and centralized. And this isn't just for futuristic smart homes. A classic real-world example is any complex dialog box and a user interface. You know the kind. You check one box and 3 other options suddenly become enabled, while another one gets grayed out. Instead of having every button and checkbox know about every other control, a single mediator object just handles all of those interactions seamlessly. But of course, there's a potential downside we have to watch out for. The mediator itself can grow into a massive, complex beast, what some people call a God object. It knows too much, it does too much, and it becomes a bottleneck. The real art of using this pattern is finding that balance, centralizing communication without creating a new monster that's impossible to maintain.
So let's bring these two powerful ideas together. When you look at both the Liskov substitution principle and the mediator pattern, you start to see they're not just about solving today's problems, they're really about designing software for the future.
So here's the quick summary. Liskov substitution tackles improper inheritance, giving us logical and predictable class structures that won't surprise us. The mediator pattern solves complex object communication, giving us decoupled, maintainable components. Both are absolutely essential tools for any software architect.
And that really leaves us with one final thought. Are principles like these just abstract rules you're supposed to memorize? Or are they something more? Are they the very heart of the craft of software development, the techniques we use to build systems that don't just work today, but actually stand the test of time? Something to think about. Thanks for joining me.